In this video, we're going to address how to measure output impedance. This has been requested a couple of times, and this will work for many circuits, but certainly not all. But this will kind of work in a general case. And we're talking about output impedance that can kind of be modeled as kind of an ideal resistor in series with an ideal voltage source. And this might be buried inside or part of a function generator or signal generator, or maybe some other kind of circuit or amplifier or something like that. And really all we need to do is to really measure how the output voltage changes as a function of the load applied. And from there we can derive what the output impedance is. Now this is our test subject for today. This is a function generator that I put together probably 25 years ago, maybe even more, maybe close to 30 years ago. And I remember building a custom output amplifier for it where I could add DC offset in either direction and make that adjustable. But I don't really remember what I had designed in as the output impedance, or if I did something specific or not. This was a long time ago. So rather than pull it apart, I figured let's just go measure what that output impedance is. So I've got the generator set up to generate a relatively low frequency, about 2 kilohertz or so. And that's kind of important because we want to ensure we're operating at a low enough frequency that we don't have to worry about reflections on a 50 ohm cable or anything like that. And we generally want to use a sine wave so that we only have energy effectively at one frequency. Where if we'd use a square wave or a triangle wave, we're going to have harmonic energy that extends up to high frequencies. And the reflections that you get off the ends of improperly terminated cables and such might distract you from the actual results. So we're just going to use a sine wave at about 2 kilohertz, which will work just fine to characterize the output impedance of this device. So in this first example, we'll use a process of simply measuring the open circuit response out of the amplifier with effectively a very high impedance load, and then measure the voltage that you get out without changing anything on the generator. Measure the voltage you get out with a load impedance applied. And once you have those two voltages, the open circuit voltage and the loaded voltage, it's a simple matter of plugging them into this equation. And the output resistance will simply be equal to the load resistance applied multiplied by this quantity, the open circuit voltage divided by the load voltage minus 1. And so let's go run that example. So the output of my homebrew signal generator is going into the oscilloscope here. I've got the scope set to a 1 megohm input impedance, which is going to give me a nice, effectively open circuit load. And I've got about a 2 kilohertz signal going in here. And I can just simply use some cursors here to make say a peak-to-peak voltage measurement for our open circuit measurement. And I can see that it's really right at about 4 volts peak to peak. So that'll be our V open of 4 volts peak to peak. Okay, to measure the loaded voltage, I'm just going to use a resistor substitution box here. I've got this one dialed into 1 kilo ohms or 1000 ohms. And I just have it connected up through a couple of banana leads into this adapter, which is going to allow me to plug it right into and load my signal generator with that. So now with that loaded at 1000 ohms, I can see my voltage has dropped, as you'd expect it would. So what we can do is go make a measurement of that peak-to-peak voltage in that loaded case where I've got 1000 ohms on the output. And it looks like we're sitting right about 2.5 volts. So I know my unloaded voltage was at 4 volts, and now my loaded voltage is at 2.5. So with that, we can run the calculation and see what the output impedance is. Okay, so let's calculate our output impedance. Our open circuit voltage was 4 volts. We divide that by our loaded voltage of 2.5 volts, subtract 1 from that, and multiply our 1000 ohm load resistance, and we wind up with 600 ohms. So, and that makes sense. When I designed this thing 25 or 30 years ago, I was probably looking at audio circuits that typically work with a 600 ohm impedance. So that all worked out well. Now there is a special case of this scenario that if the load impedance equals the output impedance, then the output or loaded voltage or loaded output voltage is going to be equal to half of the open circuit voltage. So another way to measure the output impedance is to simply vary the load impedance until the loaded output voltage is equal to half of the open, and then either measure the load impedance that you've applied or look at what it is if you're using something like our resistor substitution box. So let's do that. Alright, we already know that our open circuit voltage was 4 volts peak to peak, and we want to go down to 2 volts peak to peak because that'll be when the load impedance equals the output impedance. I'm going to turn off the voltage cursors here because since we're sitting at 1 volt per division, all I need to do is adjust my load until I get just to 2 divisions of deflection. So I'm at 1 k ohm impedance here. Let's drop it down to, I just made that 2100. Let's kind of go the other way here and push that up to, let's make that 900 ohms. You can see the voltage has come down a little bit. Let's go down now, whoops, that was 0, let's go the other way. About 800, 700, 600. Right there at 600 ohms, I can see my output voltage is now 2 volts peak to peak. So now I know that's what the output impedance is. And in many cases, this is all you need to do. But there are certain situations where this may not work. Now there are some circuits and other situations where the method we just followed may not work really well. And some of those could be, if the amplifier or circuit or generator that you're dealing with doesn't work well unloaded. It might need some kind of a load to work properly, or it might clip, or it might do something weird if it's unloaded. That would make it difficult or not possible to measure, say, the open circuit voltage. Or if the output impedance of the circuit changes with large changes in load. Right, if you go from an open circuit to some low impedance load, that's a big change in load impedance. And in many cases, the output impedance of a circuit might change with such a large change in output impedance. And what you're really interested in is what the output impedance is under normal operating circumstances. So in those cases, the method we used earlier where we measured the open circuit voltage and then the loaded circuit voltage might not be the best way. So in those cases we can actually do another method, very similar though, is just measuring the output with 2 different load impedances. Connect up one load impedance, measure the output voltage, call that say V1. Connect up another load called R2 and measure V2. And then once you've got that, you can calculate the output impedance with this formula here. And let me center that better on the screen here. Okay. Take a look at that. And you might be able to kind of rearrange this in other ways, but this formula is reasonably easy enough to solve with a calculator. So let's, even though we already know the output impedance of my little homebrew generator, let's try applying 2 different loads and seeing if we can calculate the load impedance this way. Alright, we already know that with a 600 ohm load impedance, I've got 2 volts peak to peak applied here. Let's just arbitrarily increase this to another value, say 1600 ohms, and I can adjust these cursors here to measure the peak to peak voltage in this case. And it looks to me that we're right around 2.9 or so, right about 2.9 volts peak to peak with a 1600 ohm load. So we can use those 2 values, 2 volts and 600 ohms, and 2.9 volts at 1600 ohms, and calculate the output impedance from that. Okay, we'll go calculate with those values. So R1 was 600 ohms. All right, I'll enter that in here again and multiply by 2 volts, divide by 2.9, and subtract that from the original 600. And I'm also then going to take 2 volts divided by 2.9, and then my 600 divided by 1600, subtract that, multiply. I'm left with about 592 ohms. So I'm only about 8 ohms off out of the 600, but you can see that that method works as well. And again, this will work for situations where you want to put the amplifier or the circuit in a mode where it's operating close to its normal operating quiescent point. so that the output impedance of the transistors and things like that are all what you expect them to be under normal operating conditions. So this is a little bit more of a general case, being able to just measure the output impedance, or excuse me, the output amplitude with two different load impedances, and then calculating the output impedance from that. Anyway, I hope you found this video useful and enjoyable, and got something out of it. Thanks again for watching, and I'll see you later.